Okay, hi guys. So in this particular video, I'm going to be going over a particularly tricky segment of the Module 3 lecture slides. Just so you know, those slides are sort of a Cliff Notes version of some of the concepts covered in the readings, and they also go more into the details of how you conduct the test in SPSS, how you interpret your results, and how you report your results. Those last three things are the most important things for you to get. You need to try to get the concepts as much as possible and understand all the ins and outs as well, but if there's some areas that are not making total sense, that's okay as long as you know how to run the test, when you would use it, and how you interpret your results and report them. Those are the most important things. Okay, so in this segment, I'm going to be going over how to conduct a z-test and sort of the logic behind it, and also the sampling distribution of the mean, the logic behind that, as well as standard errors. Okay, so just to recap, last week you learned that you can take an individual score and convert it into a z-score. And the nice thing about z-scores is they tell you how many standard deviations above the mean your score was in the distribution of scores. So if you have a z-score of 1, then the proportion of scores that are above your particular score will be 0.159, or 15.9% of the scores will be above your z-score of 1. Another way of saying that is that the probability of selecting a score at random that is above a z-score of 1 is 15.9%. So that in probability interpretation is very important too, because in a minute I'm going to tell you how to convert a sample mean into a z-score, so a whole sample mean, not just an individual score. And once you have the z-score, you can talk about the probability of getting that sample from the population in the first place. Okay, so statistics is all about probability of obtaining certain results in your study, so that's important. All right, so one other thing I need to mention is if you get a z-score of -1, since this is a symmetrical distribution, then the proportion of scores, or the percentage of scores that would be more extreme than -1, or I should say lower than -1, would also be 15.9%. Okay, so in order to understand how we can get a z-score for a sample mean and not just an individual score, you have to understand the sampling distribution of the mean. So I'm going to explain that now. So suppose you have a large class of 150 students, that's your population, and you have their exam scores, that's the variable, okay? You know that the mean for the whole population for these students is 80. Well, let's say you take a sample of 10 students from this 150 students, and for those 10 students, you calculate just their mean, okay? And then you throw their scores back into the pot, and then you get another 10 students at random, and you calculate their mean exam score, and then you throw them back into the pot, and you do this over and over and over again. Well, you're going to get a variety of different sample means that themselves form a distribution, okay? So you would have some sample means that are kind of low, and some sample means that are kind of high. In other words, you have a distribution of sample means. So that's what I'm talking about when I say the sampling distribution of the mean. Okay, so what that means is that with this sampling distribution of the mean, this would be like a mean, there'd be means here, there'd be means here, there'd be all these different sample means along this line, okay? So technically, the formal definition of the distribution of sample means is it's the collection of sample means for all possible random samples of a particular size that can be obtained from a population. Okay, so in practice, researchers don't really do this. It's not like we take a gazillion different samples from the population that we're interested in and keep calculating the mean over and over, or whatever statistic we're interested in, over and over and over again. That's not something we do. This sampling distribution of the mean concept that I'm talking about is a trick that we have as statisticians so that we can find the probability. Once we have this distribution of sample means, we can know the probability of getting a specific sample mean, okay? So we have actually done this. We know that when we take a bunch of samples and calculate the mean over and over again, it forms a normal distribution, which is important because that allows us to find the probability of getting certain statistics from our sample. Well, we know this because we've done it with things like dice. So say we have a dice with the standard 6 sides. Well, so there's 6 possible scores from the population. All right. Say we roll the dice twice, so our n is 2. We have 2 scores, and we calculate the mean from those 2 rolls of the dice, okay, whatever the scores were. We do that over and over and over again. We would end up with a bunch of different means, okay, and they would form a sampling distribution of the mean. And every time that we've done this sort of thing, we have found that the sampling distribution of the means forms this normal distribution, which is great because then we can calculate the area under the curve that falls beyond certain points. So that can tell us the probability of getting a specific sample mean, okay? So this is kind of a statistical trick that we have. But let's get back to the z-scores. So, the sampling distribution of the mean. Like I said, here's our sampling distribution. Now, just by random chance, sometimes we're going to happen to sample 10 students that did really, really well, okay? So we're going to have some means that are going to be out here in the extreme in terms of being very high. And just by chance, sometimes we're also going to get 10 students that did really poorly, and so we'll have some sample means that will be really low. These are going to be pretty rare, but they will occur, okay? But most of our sample means will be near the parent population mean of 80, okay? But the point is this forms a normal distribution, okay? This sampling distribution of the means is normal, okay? And there is like low scores and high scores. One important property of the sampling distribution of the mean is that the mean of those means, okay, so the mean of those individual all those individual sample means will always match the population mean. So I'm going to say that one more time. The mean of all those individual sample means taken from the parent population mean, that mean of those means will always match the parent population mean. Okay, so that is important, but it's also important to remember that that's the mean of the sample means. That does not mean that any one particular sample mean will match the population mean. Remember, we have kind of a distribution, right? So we want to be able to find the probability of getting a particular one sample mean, okay? So that's what we're kind of talking about here with this z-score test. So the standard error of the mean describes how far, on average, the sample means in that sampling distribution of means are away from their mean and therefore the parent population mean. Because remember, I just said the mean of the sample means will always match the parent population mean. So this sounds a lot like the standard deviation, which indicates how far on average individual scores will be from their mean. Okay, well, the standard error is pretty much the same concept. It's just applied to sample means in the sampling distribution of means. So the standard error of the mean is how far on average sample means will be from the mean of those sample means and therefore the parent population mean. So this is denoted by this symbol, okay? Also, it's sometimes denoted by this symbol. I think this is the one that they use in your readings. Statisticians use all kinds of symbols to mean the same thing. That's why it's important to kind of understand the meaning behind the symbols and not get so caught up in the symbols themselves. All right, so now that you know what the standard error of the mean is, you might be wondering, well, how do we even calculate that value? Well, it's based on two things. One is the variability of the parent population from which those sample means were drawn. So the more variability there is in the parent population, the more variability we'll get in our sample means. but it's also based on the sample size of those individual samples that we take. This should make intuitive sense to you that the smaller your sample size is, the more error you'll have. In other words, the smaller your sample size is, the more that mean will not match the parent population mean. The larger your sample size is, the closer that sample mean will be to the parent population mean. So if we take a bunch of samples from the parent population and those samples are fairly large, then our standard error should be pretty small because each of those sample means was pretty close to the parent population mean. So on average, all those sample means will not be very far away from the parent population mean. So here's the formula for it. It's based on those two things that I was just talking about, the variability of the parent population mean, or the variability of the parent population, so there's the standard deviation, and then also the sample size. So remember that in order to get a z-score for an individual score, we take that individual score minus the population mean divided by the standard deviation. We're literally finding out, okay, how far is our score from the mean relative to the average distance that scores are from the mean? Well, for the standard error of the mean, in order to calculate that, it's much the same way, okay? Or in order to calculate the z-score, I should say, for sample means, we pretty much have to have the same elements, okay? So we have to have the individual mean, the population mean, and we have to have the standard error of the mean, which is also known as basically the standard deviation of that sampling distribution of means. So we're going to literally see how far our specific sample mean is away from the parent population mean relative to what we can expect sample means to be, how far we can expect sample means to be away from the parent population mean on average just due to chance, okay? So let's try to conduct a z-test for sample means. So here's that example. A population of 150 students have exam scores that form a normal distribution with a mean of 75 and a standard deviation of 6. Suppose we take a sample of 36 from the parent population, okay, and had them engage in a short mindfulness breathing exercise right before they took their test. Because we wanted to see, well, maybe having them engaged in this mindfulness breathing exercise will help them do better on their test. Lo and behold, we found that that sample of 36 that engaged in the mindfulness breathing exercise had a mean of 78, which is technically larger than the parent population mean of 75. But is this a large enough difference that we can say that there's something meaningful going on here? Or is this a difference that we could expect to get just by chance? So by chance, I mean we happen to just get 36 students that were probably going to do well to begin with, okay? We got 36 students that were, you know, higher achievers, I guess you could say. So it was more a sampling problem than there being a real difference in our sample from the population because of this mindfulness activity. So the point of this test that we're about to do is we want to know the probability of getting a random sample with a mean of 78 if the actual population mean is 75 just by chance alone, okay? So we want to know what the probability of getting that is by chance, and we're hoping that we have, you know, a real effect going here and that it's not just due to chance. So let's actually, I'm going to skip that previous slide, but you'll want to look at that later. So here's the example. We're going to calculate the z-score, but first we have to get the standard error of the mean, okay? So we have to calculate this first so that we can plug it into this z-score formula. So this is the standard error of the mean. This is that denominator. This is how you calculate that, okay? So when you calculate that out, you end up getting a standard error of the mean that's 1. And again, you take your standard deviation divided by your square root of n. Okay, so all these elements are up here, okay, in this problem. I just filled in the pieces. And I ended up finding out that my standard error of the means, the denominator of my z-test, is 1. So that means that on average, just by chance alone, we can expect sample means to be 1 point away from the population mean. All right? So what we want to do is we want to see if our specific sample mean is farther away from the population mean than what we can expect by chance. Because we want to be able to say that there's something meaningful going on with the mindfulness and that it's not just a chance fluke finding. All right, so when we have that standard error of the mean, we calculate it as 1. If we plug it into the z-score formula, we ended up getting a z of 3. So our specific sample mean is 3 standard deviations above the population mean in the sampling distribution of means. So out of all the sample means that we could get from the parent population, ours is pretty extreme, okay? So ours is pretty extreme out there. Note, that's 3 standard deviations away from the mean in the sampling distribution of the means, okay? Not the parent population mean. The parent population mean has a standard deviation of 6, okay? That's the distribution of scores in the population, all right? So you can find out the probability of getting a z-score this extreme, all right? So if you go to this particular website, I can put in my z-score of 3, all right, and then compute the p-value. All right, it's telling me that the probability of getting a z more extreme than that is pretty low, okay? So in other words, it's pretty rare for us to get a sample mean that is this far away from the parent population mean just by chance alone, okay? So the conclusion I would draw from this is that probably the difference between our sample mean and the parent population mean is not due to chance, because our difference between the sample mean and the parent population mean was larger. It was 3 than what we can expect by chance. Okay, so that's important. Now, one other thing I want to go over before I conclude this video is that many of the statistics that you will learn about in this class have their own sampling distribution. So we just talked about the sampling distribution of the mean, but literally you can get a sampling distribution for pretty much any statistic, okay? So you could get a sampling distribution for correlations. So what that means is if I took a sample and got the correlation between, say, studying time and GPA, and I did that over and over and over for a bunch of different samples, that would form a normal distribution. And then I could see the probability of getting a specific correlation, okay? So that sampling distribution doesn't just apply to the mean, it can apply to any statistic, and it's going to apply to pretty much all the statistics that you will learn about in the next class. And that's helpful because if we know what point along the sampling distribution of that statistic our specific statistic that we calculated in our specific sample, our specific study is, if we have that, then we can know how extreme it is, how rare it is. All right, the other thing I want to go over is that standard error is also another thing that's important and will come up over and over and over again. So here we were learning how to calculate the standard error of the mean, but you can get a standard error for pretty much any statistic, and it describes how far off you can expect sample statistics to be from the parent population statistic with any given sample size just by chance alone, okay? So hopefully, if you know how far off statistics and sample statistics will be from the population statistic by chance alone and on average, then you can see if your particular statistic that you calculate is probably not due to chance, okay? All right, so I'm going to stop there and